theoretical physicist, and today in this talk of randomness and large numbers, I'll not really talk about what I work on, but I'll try to give you some basic ideas about the subjects via very simple things. Okay, so let's start with a very simple setup. Okay, so suppose I have this lattice kind of a thing, a structure basically, and I drop a ball from on top of this structure. And at each this top vertex of the triangle, the ball can go either to the right or to the left. Okay, and then I let the ball run through and let it collect in one of these boxes. Okay, so where will the ball end up? Okay, so you can answer. You can answer. Some of you may answer the left box or the right box or somewhere in the middle. But the point is, everyone would be right because the where the ball ends up is completely random because it can take any one of the paths and just go and sit in one of the boxes. Okay, so the final result is completely random. But instead, what if I have a collection of balls? Okay, so this is the setup now. It's the same structure which I showed you earlier. So I have a funnel-like thing where I like trap a lot of balls and let them go. Let them go and I let them collect in the boxes that I had shown earlier. Okay, so this particular setup is called a Galton board. So it was invented by Sir Francis Galton, who was an Englishman, but he was this lot of things. So I kept just this to show you that nowadays, I mean, you don't expect people to do so lot of things together. I mean, he did quite a lot of things, and he was brilliant in all of them. Okay, so yes. So what happens to these balls? Now, when I let them drop these balls, what I see is you go again. So it drops, and every time it drops, the balls collect in a way that it forms a particular shape, right? It always there's this outline. It always ends up something like this. So it's interesting, right? Because we just now saw that at a single ball level, everything is completely random. But when you are taking a collection of balls, you are getting some shape, some particular shape every time. Okay, so what's going on? So now let's do a little bit of counting. Okay, suppose I have this one triangle and the boxes are just after my first level. So I'll call the levels as the levels of horizontal triangles. Okay, so in what way can it collect in the two boxes? So then I have two boxes, right? So in what way can it collect in the two boxes? So it can either go this way or it can go this way, and it can collect here in a. I mean, there's this one path. It can go here, or it can go here in this one path only. Okay. But what if I have now two levels of these triangles? And so how many ways can the ball go to positions A, B, and C? So can somebody quickly answer? Anybody in the audience? So I'll just show you one. So this position A goes only by one path, only because if it goes like this, it cannot reach A. It can reach A only via one single path. So B, C, can anyone guess or say how many ways it can go to B or C, end up in B or C? I didn't hear. So is anybody answering?
Two, sir.
It's very simple.
Only two balls can go to B maximum.
Yeah. Yeah. Did somebody say two ways into B and one way to C, right? I heard.
Yes, sir.
I heard correctly. Yeah. So you are correct. So it can go to A or C in only one way, and it can go to B in two ways. Or it can come from here or it can come from here. And if I increase how do I remove this? Anyway, now say I increase one more level of the triangle. Okay, so then again at the ends it can go in one way, and to the middle you now see it goes this one. It can go in three way. The ways are marked with green, and again to the yellow also it can go in three way. Okay, so it appears as you just go on keep adding on the levels, it keeps forming this pattern. So one and then one and then one two one, and so there's something about in this pattern. So have any of you ever seen this pattern before? Is no the answer?
Yes, sir.
You have seen this.
Yes, sir. In mathematics.
It's the Pascal's triangle. Okay. So what happens is, uh, so there's one here, and whenever you go to the next step, what you do is this carries on, and the next number is basically the sum of the things in the previous two. So here two is the sum of one, and then again you get one, and then here it's one. One plus two comes three here. Two plus one, three here, and again one here. Okay, so as you keep increasing the levels of these triangles, you generate this Pascal's triangle, okay, and it goes on, okay, and the number of balls at a particular box, if you have, say, a large number of these levels, is actually proportional to the number of paths that can lead to the box. Okay, so you have a maze, and you calculate the number of paths it can go to one particular box. So your net weight, it will be of the number of balls. Is anybody saying something? No. Okay, so the number of balls in that particular box would be proportional to the number of paths that can lead to the box. Okay, and so here I have plotted this number of these numbers. If I had 9 levels, and you automatically see the pattern which we were seeing in the Galton board experiment, right? This pattern emerges. Okay, already. So basically, there are still the fluctuations. You can see the red line and these are not quite same. But as you keep on adding the number of balls, these will become smoother, and you will have something which is a Gaussian distribution. Okay. If you're doing physics anytime later after your 12th boards and so on, this is something you will encounter surely. Everybody does, and it's right. It's named after Carl Friedrich Gauss, the famous mathematician. Okay, so now this is a very important concept in which is called random walk, which has numerous applications in physics, mathematics, biology, economics, ecology, and everything. Because it's quite inherent in these subtopics. Okay, and it's also often called a drunkard's walk, because imagine you have a drunk person coming out of a bar and he doesn't remember where he'll go to. Okay, so he goes forward some distance, and then he remembers, no, my home is that way, I'll go there, and then he goes the other way, and then again at some point of time he remembers, oh no, I need to go the other way. So that's why it's also called a drunkard's walk. And so the takeaway message from here is random events basically lead to predictive patterns, and these predictions become better larger the number of events or subjects. Okay, and from there I'll quickly jump to something which is closely related to stat phase. So basically, in a solid, liquid, or gas, you have a large number of molecules. So what do? You don't solve Newton's equation for all the particles. Okay, so there are a huge number of particles, and you can't calculate the Newton's F equal to ma for all of these. Okay, but again, you can predict the macroscopic behavior. Macroscopic behavior, the emergent behavior which we see. Okay, you can predict that behavior from a collection of a large number of molecules.
Ian,
This is,
Ian, can you finish in the
yeah,
next 2 minutes?
yes,
Okay.
sure. So it's a collection of large number of particles. You can predict this emergent behavior when you have a large number of particles. Okay, and this is, in a way, we do is similar to the counting problem which we just saw, and this is the basic behind the idea behind equilibrium statistical physics. Okay, so if you have the total number of particles, volume, and energy of a system of particles, say a large 10 to the 23 order of particles, and you have to count the number of ways in which they can be arranged so as to fix these constraints. Okay, so NBE, you fix them, and you can see how many ways you can put them into these kind of boxes. Okay, and the number of ways you write it in something called W, say. And then you can define a function which is called an entropy. I think you must have heard this in sci-fi movies and so on. So entropy you define as k log of omega, W. And then when you have this S, you can calculate specific heat conductivity, predict phase transitions, and everything from it by taking derivatives or integral relations from this. Okay. So this is called the Boltzmann prescription, and so that's all for my talk. So the take-home message is basically what appears random to naked eye is always not completely random. There's hidden information that can be extracted, and the law of large numbers, which we physicists typically call the thermodynamic limit, can lead to very predictive laws.
Okay,
Okay.
let's have let's have questions.
Sir, like what type did you feel interesting so that it attracted you to do research on this?
He said that what did you find interesting that you are doing research on this? What was the motivating part?
Okay, so the point is, for this example, you see, you have a liquid, you have a large number of liquid molecules. So you don't solve the Newton's equations, right? You just do what you see is you count. There's a number of counting patterns. This counting can be very tricky and very difficult. So I mean, to predict new phases of matter, okay, if you are doing these exercises and there are some things which you haven't seen yet, and that you can predict from here, the kind of phase transitions in matter. So water to water vapor is one kind of phase transition. There are numerous other phase transitions, and magnetization, you have magnets and non-magnets. Okay, all these you can predict from here. So it's basically learning trying to learn what is in the basic, what is in the, I mean, how these matters change among themselves and so on. The different states of matter, for
O-
example.
Okay, let's thank Ayan for such a wonderful talk.